Chapter 12 is on gas laws.
Mhm.
So the basic assumption in kinetic theory for gases are they are particles that are tiny and far apart, no interactive forces, rapid random motion, elastic collisions, and the average change of energy is that directly proportional to temperature? Alpha temperature. Gas particles assumed to have no attractive or repulsive forces between them, as mentioned before. They're free to move inside their containers. They expand until they take both the shape and volume of its container. Collisions of rapidly random moving particles are completely elastic. Kinetic energy is transferred but not lost. There are four variables to describe a gas: pressure, volume, temperature, and amount. These are all the units. You want
Boyle's law equals the volume of gas varies Boyle's law. The volume of gas varies inversely with the pressure. As one goes up, the other goes down. Charles' law, the volume of a gas is directly proportional to its Kelvin temperature if pressure is kept constant. Gay-Lussac's law, quite a good name. There is a direct relationship between the temperature and pressure of a gas. If one increases, so does the other. If volume is held constant, P1 equals P2, pressure 1 equals pressure 2. Combined gas law, it includes all of them. So this is Boyle's, Charles, and Gay-Lussac's law.
Yeah, okay. Avogadro's hypothesis. Okay. All right. I'll be right back. Yeah, sure. Equal volumes of all gases at the same temperature and pressures contain the same number of molecules.
Yeah.
1 mole of any gas at STP is 22.4. Remember that. That's important. Use that in Mole Island especially. Dalton's law of partial pressures. The sum of all the pressures is equal to the pressure of the total. So, as you can see here, the pressure in air is equal to all of these pressures combined: O2, N2, AR, argon, water, dioxide. Now, diffusion versus effusion. Diffusion is the spreading out of molecules from a region where they are concentrated is high to where their concentration is high to a region where the concentration is low. For gases, this is high partial pressure to low partial pressure. So that's why an example is water. So in a cup of water, the water molecules will diffuse, so it'll be even. So like not one side will have all the water. Effusion, the diffusion of a gas through a tiny hole or holes. Examples of these are gradual deflation of balloons and tires.
Graham's law of diffusion. The rate of diffusion is equal to and inversely proportional to the square root of its molar mass. Graham's law of diffusion is the rate 2 over rate 1 equals the square root of mass 2 over mass 1. Chapter 13, electrons. Atomic theory and models. Dalton made his in 1803, thought that atoms were like smooth, hard bowling balls or pool balls, billiard balls, that could not be broken into smaller pieces. Atomic theory, Thomson's model, Thomson in 1897, suggests that atoms had negatively charged electrons embedded in a positive sphere, kind of like a cookie with chocolate chips in this side, in the middle. Atomic theory and models, number 4 or whatever. Rutherford, 1911, was surprised that few particles were deflected strongly. This led him to the idea that atomic model was the nucleus positively charged in the center with electrons going around it, as shown. So Niels Bohr came up with his idea in 1913, he said that electrons had specific circles that they had to go around, sort of like
planets.
Yeah, sort of like planets. Bohr's model is the one that
we said this.
Yeah, okay. I just said that. The cloud model is the one that is the modern atomic model. It shows the nucleus, which contains the protons and the neutrons, and is surrounded in a cloud or a sea of electrons. This is just the pictures for all of them. Heisenberg's uncertainty principle states that you cannot find both where an electron is and where it is going, but you can only have one or the other.
Quantum mechanical model or wave model. So small, dense, positively charged nucleus surrounded by electron clouds of probability, just like in the previous model, in the Schrodinger's model, the modern model. This does not define an exact path an electron takes around the cloud, but in the electron cloud, the volume in which the electron, it's found 90% of the time. So you're 90% likely if you like drew a point somewhere, an electron will be there.
90%.
Mm-hmm.
Energy sublevels. So the second quantum number, the energy sublevel is equal to the value of the principal quantum number, n, for that level. Sublevels are named in the following order: S, P, D, F. These are on the periodic table. We learned about these earlier. The number designates the shape of the electron cloud. The
L.
yeah, that's the L number.
Orbitals, a third quantum number, m. The space occupied by a pair of electrons in a certain sublevel. A sublevel, S, is the first one orbital, P, 3 orbitals, D, 5 orbitals, F, 7 orbitals. Each orbital can hold 2 electrons, as in S, and M represents the number in which space of an orientation in space of the orbitals, x-axis, y-axis, z-axis.
The fourth quantum number distinguishes between the electron in the same orbital. Distinguishes between the electrons in the same orbital. This describes the electron spin as either clockwise or counterclockwise. The 3 important rules to know. Aufbau's principle. Each orbital and sublevel on the lower energy levels must be occupied before moving to higher energy levels. So you must fill your S before you can go to P, D, and so on.
Like the boxes.
Yeah, an orbital is just another fancy word for like the boxes.
Mm-hmm.
The Pauli exclusion principle, a maximum of 2 electrons may occupy an orbital. Paired electrons must spin oppositely. And Hund's rule is the one that Mr. Burnham described as the boys' bathroom rule. Single electrons must occupy separate orbitals in a sublevel. So no pairing occurs until all the empty orbitals exist in a sublevel, have at least one. So you fill this box, then one over here, then one over here before you start doing the opposites.
Exceptions to the Aufbau rule. Exceptions are the full shell stability, half shell stability, and these are examples of these ones. So chromium is here, copper is here. So what these want to do is they want to get a full D5 shell. So they'll steal an electron from the 4s shell. And so instead of it being 4s2, 3d4, it'll be 4s1, 3d5. Same with this, instead of 4s2, 3d9, it'll be 4s1, 3d10. And then these are also. Filled energy sublevels are more stable than partially filled sublevels. So that's why the octet rule, that's why they all want to get to 8 electrons. Half filled are not as stable as filled, but are more stable than other configurations, just how the chromium ones, they want to get there. So the half D filled still, so D5. All right, chapter 14.
Chemical periodicity.
Periodicity.
Whatever that is. Yep. The periodic law states, when elements are arranged in order of increasing atomic number, there is a periodic repetition of their physical and chemical properties. The periodic table can be split up into a few sections with 1, the representative elements. So that is the first section. That is group A. And the last section is the second group, which is group 8 at the very end. And those are the noble gases. That's the perfect electron configuration.
This is
That's the
gonna
one
be
that
really loud.
all of the other ones want. Okay, go.
Oh, ow.
You're opening it backwards, buddy.
Yes, exactly. Oh, it doesn't work on this. Okay, never mind. All right, go.
Okay. So on. Group number equals the number
Go
of
broad.
valence electrons. Want to just like
Okay, never mind.
okay.
All right, we'll keep going. Maybe I can use my key.
Transition metals, aka D block. So that's the D
It's not working. Just keep going.
D orbitals, and the inner transitioner metals is the F block. So in the periodic table, the group of atoms that has the Orbitals.
Yeah.
Halogens gain 1 electron to become a halogen gases are the 7th group, and they gain 1 electron to become a noble gas. And whenever a metal and a halogen combine, it's called a salt, not the same as table salt.
Well, no, it is this
Well,
because
yeah, but
table salt is an example of it.
yes,
Yeah,
but yeah.
40.2 periodic trend.
Trends, Chinks.
Okay. 4 chemical and physical properties: atomic size, ionization energy, ionic size, electronegativity. I know. I
No.
can't. Can you try? No. Well, don't break my keys. The trends on the periodic table. Well, yeah, we just said that. So atomic radius is when the atom, the ion, the atom. These are atom ions. So the lower you go, the bigger they get, and then the diagonal you go, and the more you move that way, the smaller it'll get. So francium down here
There's a whole.
is the biggest atom with the biggest radius, and then helium is the smallest. Oh no, you just get the outline. Oh, you might need a knife. Oh, well. Okay. As you descend, electrons are added to. Okay, well, now I explain this. That energy to remove a mole of electrons from a mole of gaseous atoms is ionization energy. Oh yeah, you can go.
Okay, the number of easier to remove electrons is the valence electrons. These are the ones at the very end. So this is a picture of the ionization energy, which is a periodic trend. So as it goes that way, the ionization energy increases, and as it goes up, the ionization energy also increases. Ionic radius, however, quite similar in that it goes the opposite, which is not similar at all. It actually increases going down and decreases going that way. So just look at the picture. Looking. So electronegativity. All right, guys, pay attention. Electronegativity equals the tendency of a bonded atom to attract electrons to itself. That's like basically it's just its strength of being able to pull other electrons to it, stick to it. So more electronegative, more electronegative, and the more electronegative an atom is, the more it wins the tug of war game, and the more it pulls other electrons to its side, to it. So electronegativity, this increases that way and increases that way, like that.
So the summary of the trends: electronegativity. So you can see it decreases down, increases as we go right. Ionization is the same. Atomic radius, inverse, decreases, increases. Nuclear charge increases, and the shielding is constant. Well, we don't learn about nuclear charge and shielding.
Yeah.
Okay. Chapter 15: ionic bonding and ionic compounds. These are more recent chapters, so
Hopefully you know them better.
Yep. Electron dot structure diagrams. It's a way of keeping track of valence electrons. Gosh, the sun's right here.
Correct.
All around. Okay.
Flip. Pause while we take a quick Kiwi. Oh, now the sun is like right in our eyes though.
It's not for me. The trees there.
Okay, just go.
All right. So it's a way of keeping track of valence electrons. So you write them. You put the symbol. So for this one, X usually just means like the atom that we're using. So if we want chlorine, we put Cl. So you put 1 dot for each valence electron. So chlorine would have 7, and you don't pair them until you have to, according to Hund's rule. So we put a dot here, 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 here. You should also put them as far apart as possible, like, that's the rule. And then you go here, here, here. So you only have 7, so exclude this one because chlorine has 7 valence electrons. You're up. Okay, I guess I'm going. Transition metals, cations. So the charges for transition metals they vary.
Light them up. 18 valence electrons is known as a pseudo-noble gas. This is what the I think it's intertransitional metals, but it's the
Mhm,
center block
Yeah,
at the
intertransitional.
very end of it. Those are pseudo noble gases. Close to noble gas, but it's not really a noble gas.
The next best thing.
Yeah, exactly. It's what they really, really want.
Mhm,
Pseudo noble gas configuration.
We talked about this.
Okay, we did just talk about that actually. So all atoms want to get a noble gas configuration. That's what makes them happy. That's 18 valence electrons. That's the octet rule.
8.
Oh yeah, sorry, 8, not 18. That was quite puzzling. How many of those do you have? Next.
Called the octet rule. This is what all of them want. They want 8.
I already said that.
Okay.
Okay, so ionic versus molecular compounds. These are just some characteristics. So, like the representative unit for an ionic compound is formula, but for a covalent, it's molecular. You can kind of look at this on your own time.
I guess the most important ones are those. They're metallic and non-metallic for an ionic. Covalent, 2 non-metallics. Solid versus solid, liquid, or gas.
I'd say the first 3 are most useful, and then melting point is also useful. Yep. But do they conduct? Conducting electricity is allowing charges to move. In a solid, the ions are locked in place and cannot move. Ionic solids are insulators. When melted, the ions can move around freely. Melted ionic compounds can conduct electricity. They dissolved in water. If they dissolve in water, they also can conduct electricity. This is called an aqueous solution. Metallic bonds. How atoms are held together in the solid. Metals hold on to their valence electrons very weakly. So think of them as positive ions floating in a sea of electrons. Alloys. We use lots of metals every day, but few are pure metals. Think laptops, think phones, those are not pure. Alloys are mixtures of 2 or more elements. At least one has to be a metal. These are made by melting a mixture of the ingredients, then cooling. Brass is an alloy. Next slide.
Metal alloys. So these are substitutional alloys. Some metal atoms replaced by others of similar size. So like, see in this picture, copper and zinc. So this makes brass. But then some common stuff is like your gold chain. That's probably not all gold. There are probably some other metals.
Like carrots.
Exactly. Wait, what? Okay. Well, you get the idea. So,
This is just the difference between interstitial and substitial.
yeah. Okay. That's basic. Okay. Chapter 16,
Already.
covalent bonding. Man, this is it, guys. Last chapter.
Yeah, guys, let's go. The nature of covalent bonding. Objectives for this chapter: use electron dot structures to show the formation of a single, double, and triple covalent bonds, which are pretty simple. How does H2 form? Well, the nuclei repel, just as you would guess for the Vesper theory, but
Vesper.
they are attracted. The electrons are attracted, so they have to share the 2 electrons, but the atoms, as you can see,
Right half the
are
bag.
forced apart. Covalent bonds, on the other hand, absolutely, my friend.
Yes, sir.
They are nonmetals, and the nonmetals hold on to their valence electrons. They can give away electrons to bond. So like, getting stolen or something like that. But they still want the noble gas configuration. They get it by sharing valence electrons with each other. By sharing, both atoms get to count the electrons toward a noble gas configuration. So this is better for both atoms. However, it is weaker for both atoms. So an ionic bond is stronger. So this is how fluorine has 7 valence electrons, just needs 1 more. It's just so close. So this other fluorine comes up and it has 7 valence electrons. So it just needs 1. So why don't they just, share electrons
Oh, that's what they
and,
do.
combine.
Exactly.
Yeah. They both end happy with full orbitals at the end. Ever after, happy ever after.
Mhm.
This is how to show how they formed. I mean, yeah. It's like a jigsaw puzzle. You put the pieces together to end up with the right formula, the right ending. Carbon is a special example, and it can share 4 electrons, which is quite the upgrade from the other regular 3. Another example show how to water is filled up.
Here's water, people. Hydrogen has 1. Oxygen has 6. So this one guy comes up and he wants to share. So he shares. So that becomes hydrogen has 2. And then oxygen, but oxygen is not completely satisfied. So another guy comes up and then he shares. And so he has like 2 people, he's practically cheating on the first hydrogen, but still being perfectly happy. And they're all happy.
Because hydrogen only wants 2.
Hydrogen only wants 2, and oxygen wants all 8. Multiple bonds. Sometimes atoms can share more than 1 pair of valence electrons. A double pair is when atoms share 2 pairs, or total of electrons. A triple is when atoms share 3 pairs, 6 total of electrons. So these are all the diatomic molecules. So carbon dioxide. So this one, carbon has 4. It wants 4, so it can get all 8. Oxygen has 6. It wants 2 more, so it can get 8. So carbon attaches to oxygen to form 1 pair, and they'll probably form another, but we'll see. So another oxygen comes in, and they also start forming pairs, and so they have to share more. So the only solution is to share. So they alter electrons, but without changing the configuration. Well, they are changing. So see, they keep altering. So now it has all 8. All 8 are needed. So this is like a little Venn diagram. And then also oxygen has all 8. And this oxygen has all 8. So how to draw them? Well, we showed those how to draw.
Yeah.
Sorry. Here's another example.
You guys can kind of run through those problems if you want.
Coordinate covalent bond. These are important. Go.
The objective of this section is to describe and give examples of coordinate covalent bonding, resonance structures, and exceptions to the octet rule, all 3. Starting off with coordinate covalent bond. This is when one atom donates both the electrons in a covalent bond to reach the octet rule, the happy 8. So see, oxygen here is donating this one. Wait.
Yeah.
Yeah. I see. See, it's donating this one here and this one here.
Okay. So that's the first step, though.
Yeah. Now here, see, he's giving these 2 right there.
So if you leave it off here, you have carbon with only 6, but oxygen has all 8. So what is oxygen gonna do?
What to do indeed.
He's gonna be that great pal.
See, he's giving all these right here.
He's basically paying for the bill.
Mad genius, paying the full bill.
Exactly. So that's how the dot structure is drawn, but it's shown as the arrow. So that is where the coordinate covalent bond comes into play.
Yes, sir. Resonance is a little simpler. It's when more than one valid dot structure is possible. So
valid. It has to be valid.
Yeah, it does have to be valid. That is one of the restrictions. But this is possible. Consider the 2 ways to draw ozone.
Not the ozone layer.
One.
It is never mind.
Never mind. It is the ozone layer, but don't think of the ozone layer because you don't get distracted.
But it is the ozone layer.
But does it go back and forth? It is a hybrid of both, like a mule. Disgusting hybrid, inbred monsters.
Okay. Nice.
So these are exceptions to the octet rule. For some molecules, it is impossible to satisfy the octet rule. Usually, when there's an odd number of valence electrons, this is what happens. So I got this question. So NO2 has 17 valence electrons. Because the N has 5 and each O contributes 6, then it's odd. It's uneven. They can't get to the perfect 8.
I messed up.
It's impossible to satisfy the octet rule in this. So the stable molecule does not exist. Exceptions to octet rule part 2. Consider electrons as small spinning electrical charges. All right. Once you've got that image in your head, and create a magnetic field. When paired, they cancel each other because they are spinning in opposite directions.
They are. More exceptions.
Well, easier stated exceptions.
Bonding theories. So Vesper theory,
Separate.
okay, same thing. So we only use these three. Basically, we got two, that's 180 degrees. We got three, the things between them are 120. And then we got four. What are they called? All I know is that this one was a tetrahedral.
They're electrons.
And they're 109.5 degrees.
Wait.
Oh, yeah, that's what they are called. Okay.
Tetrahedral, trigonal.
Linear, trigonal, planar, tetrahedral.
Wait, you can't see your fingers. You have to go linear, trigonal. Wow. Trigonal planar has 3. Tetrahedral has 1, 2, 3, 4. Trigonal.
No, we don't need those.
Yeah, you don't.
Those are, that's basically a pyramid, a triangle, a line.
Yeah.
You can.
Okay, section 16.3. This is the best section in my opinion. Polar bonds molecules. The objective of this section is to use electronegativity values to classify a bond as nonpolar, covalent, polar covalent, or ionic. Sounds like a thought, it's not. Bond polarity is when 2 different atoms bond covalently and there is an unequal sharing. The more electronegative atom will have a stronger attraction and will acquire a slightly negative charge, called a polar covalent bond, or this is called a polar covalent bond, or simply a polar bond. Bond polarity. Only partial charges, much less than a true +1 or -1, as in ionic bond. So if it has a plus on one side and negative ion on the other side, that is bond polarity. The positive and minus signs with the lowercase, whatever those things are, the positive and negative.
Delta? No, that's not delta. That's, I don't know,
They
actually.
denote partial charges. So basically they cancel each other out because this positive is pulling that way and this negative is pulling the other way, and a lot of theta. So this is just another picture of that. See covalent bonds like that, polar covalent bonds, a little bit whack, and ionics are mean because the ionics, yeah. Bond polarity can also be shown with this arrow, which points to the more electronegative atom right here, which is, like we said earlier, the one that's negative.
Mhm.
Yeah. So this is the electronegativity
It
chart.
goes from left. Wait, yeah, it goes from here, that thing, to up here. Polar molecules. Polar bond tends to make the entire molecule polar. Areas of difference. HCl, hydrogen chloride, has polar bonds. Thus, it is a polar molecule. A molecule that has 2 poles is called dipole.
Ooh.
So these are examples. Bond dipole, bond dipole. The sharing of electrons ties atoms together in the form of molecules and isolates the electrons for further interactions. Intermolecular forces, as discussed earlier, exist because covalently bonded molecules that cause them to form solids and liquids. The weakest of these are like, what is this?
The weakest intermolecular force is the London dispersion force. Not to be confused with this London bridge right here.
Oh, I was confused.
This man's a genius.
Okay. They produce momentary dipoles that hold the molecules together. They're caused by the temporary shifting of the electron clouds through interactions between molecules. For an homologous series, CH4, C2H6, C3H8, etc., polarizability increases with molar mass, which is greater electron cloud shift.
Not sure we learned much about that.
We didn't learn much about London dispersion. Here again is the halogens. These are some of the diatomic molecules. Dipole interactions. Can we talk about that? Oh, wait. Okay, dipole interactions occurs when polar molecules are attracted to each other. Dipole interactions happen in water. Positive regions of one water molecules attract the negative region of another water molecule. Hydrogen bonding. When a hydrogen is covalently bonded to a highly electronegative atom and is also weakly bonded to an unshared electron pair of another electronegative, The hydrogen is left very electron deficient. Thus, it shares with something nearby. Types of intermolecular forces and relative strengths. So the weakest, the strongest, these are examples. We only learn about hydrogen, dipole, one of these, and dispersion forces or London forces.
Attractions and properties. Why are some chemicals and gases, some liquids, some solids? Well, it depends on the type of bonding. So, network solids is a special type of molecular solid, melts very high or not at all. But attractions properties. So this is one of the last slides, I think, actually. So the network atomic solids, some covalently bonded substances do not form discrete molecules. For example, diamond is a network of covalently bonded carbon atoms. So that's why it's like so beautiful like that. But graphite is a network of covalently bonded carbon atoms as well, but it looks a bit different because they're not stacked as perfectly like that.
Smash, pass.
The end.
All right, that was it.